Drip Drop Acid-Base Experiment, Lab 24. Introduction. The purpose of this lab is to investigate the simple reaction between two different acids and a base. We will be counting the number of drops of sodium hydroxide that are needed to react completely with all of the acid. The starting acid and base solutions are colorless and clear, and the final products are colorless and clear. To monitor the progress of the chemical reaction, the acid-base indicator phenolphthalein will be used. Phenolphthalein is colorless when acidic and pink in color when neutral or basic. In this activity, we will know that all of the acid has been consumed by the base when the test tube solution starts to turn pink. We can monitor the progress of the reaction so that a single drop of the base results in a sudden change from colorless to pink. At that point, we will know that all of the acid has reacted with the base. You will need to count the number of drops of sodium hydroxide that are necessary to neutralize two different acids. Find the relationship between the sodium hydroxide drops necessary and the coefficients in the balanced chemical equation. Objectives. Translate word equations into chemical formulas. Count the number of drops of sodium hydroxide needed to completely react with different acid samples. Calculate the average number of drops of sodium hydroxide needed for each acid, and relate the number of drops to the coefficients in the balanced chemical equations. Materials. For this lab, you will need burette clamps, 2 burettes, sulfuric acid 0.1 molar, hydrochloric acid 0.1 molar, and sodium hydroxide 0.3 molar, phenolphthalein indicator, pipettes, ring stands, test tubes, and test tube rack. So, safety first, we'll follow standard safety protocols for this lab, and we'll be extra sure to protect our skin and eyes when using strong acids and bases, even though they are diluted for our purposes in this lab. Translate each of the word equations shown below into chemical equations. This is step 1 of our procedure. Hydrochloric acid plus sodium hydroxide yields sodium chloride and water, and sulfuric acid plus sodium hydroxide yields sodium sulfate and water. We're going to balance these equations. Copy down data tables 1 and 2 in your notebook and leave room for note-taking. So this is the data table from your lab binder. And what we'll be doing for this lab is that each team will be running 2 trials of hydrochloric acid at 2 milliliters volume, 2 trials of hydrochloric acid at 4 milliliters, and 2 trials of sulfuric acid at 2 milliliters. Next, they will take the average of their 2 trials and enter this data into our shared class data table. This is the data that will then be used to determine a class average of the number of drops of sodium hydroxide needed to consume each volume of acid. And for the purpose of analyzing data and drawing conclusions, we will be using the class average data as our data source. So this is what our class average data tables look like. So we're going to clean and rinse 6 test tubes with distilled water, and then we're going to obtain 10 to 30 milliliters of sodium hydroxide solution in a small beaker. Now we'll be using burettes for this lab, and you've never used one before, so here's how burettes work. So to give you an idea how big they actually are, here's my ceiling. I'll come all the way down. There's the top of the ring stand, right? And although they are quite tall, they're very narrow, and this particular burette, these ones to this pair, hold a total of 50 mils. That's it. Each one of these sections is a milliliter, which for size comparison, this is a 50 milliliter beaker. So the volume of this tiny beaker that fits right in the palm of my hand is the same as this big tall burette. And the way they work is this is called a stopcock. And if you turn the stopcock to open it by going this way, you'll see that it will start to first drip slowly, see? But you can also make it go fast if you want. The way you measure from a burette, I have to go to the other one at this point. We should make sure it's totally turned on. So the way you measure using a burette is you kind of have to think backwards math. So if you look right here, I don't know if you can see in this light, this burette, let's make it go right to the 47. Okay, so I'm just going to turn it, and you're always going to read from that bottom of the meniscus. So watch closely, it'll start to drip right around here. Go slow, right there. Okay, so say you want, as in this particular lab, 2 mils. Okay, so that means you have to go from the 47 to the 49. So it's a little backwards math, but it's not hard. So you're just going to very slowly turn the stopcock. You can go slower if you need to. Slower. Right at the bottom of the meniscus, right there. That's your 49. 47 to 49, that's going to give us 2. Actually, it looks like it could use one more drop. Real close. See if I can get one more. Right there. Perfect. And that's how they work. And I'll give you a close-up of the end of it so you can see how it drips. Pretty cool. Procedure Part 1, Trials 1 and 2. You'll be using a burette. Add 2 milliliters of 0.1 molar hydrochloric acid to the test tube. Add 2 drops of phenolphthalein indicator. Using a pipette, slowly add 0.3 molar sodium hydroxide to the test tube, counting each drop. When the solution changes from clear to pink, record your results. Now, if you can get it a very pale pink from clear to just pink, you'll know you've got very, very accurate results. Then you're going to repeat the procedure because we're going to do this particular part of the procedure 2 times, trials 1 and 2. Calculate the average number of drops of sodium hydroxide from trials 1 and 2.
Oh, look at that! Are we supposed to shake it?
Yes.
Give it a little shake every time. Yep. Good.
When you shake it, it goes away.
Yep, when you shake it, it goes away. So you're going to have to keep doing it.
Go! I see the purple. Like the purple.
Let's go. Let's go.
That looks like 2.
We're up to 4.
All right.
Exactly.
It's going to be a lot more than 4. You're going to be a while.
But we did it.
Shake it.
Oh, never mind. Yeah, we don't. No, we don't. We have to clean this up and we have to restart.
Shake it. Look at this.
What'd you say?
We're raising awareness.
That was 2 that time.
Oh!
Yes!
So what did you get up to?
There you go.
What did you get up to?
Yeah, you girls are going to want to watch because this part's the fun part. About there. Almost.
What?
What in the world are y'all doing?
I don't even know what they're doing. But Miss Danny.
There you go.
24.
24. So our average number of drops was 20. Procedure Part 2, Trials 1 and 2. This time we're going to use our burette and add 4 milliliters of 0.1 molar hydrochloric acid to the test tube. add our 2 drops of phenolphthalein, use the pipette and add 0.3 molar sodium hydroxide drop by drop, counting each drop. When it changes color, we're going to record results. And then we're going to repeat the procedure, calculate the average of drops, and add that to our class data table.
Science.
Hold off until we learn.
You guys ready? Go on to the next one.
Oh, under that.
Okay, how many
They're still dangerous. Okay.
Is there liquid in here?
Yes, they are.
Go grab that. This line right here.
Yeah.
Where I put this? Right here.
13, yeah.
How dangerous are the chemicals after doing it?
Not really, but still, you don't want to mess with it.
Sodium hydroxide.
But you need to set a precedent.
Sodium hydroxide?
Yeah.
Put it in there.
Give it a good vigorous shake. There you go.
I think that's good.
Just so that there's something.
Literally nothing
No, we're
dropped
good.
when you said that.
We're good.
No. Look at it. It's not there yet.
Yes, it is.
No, it's not.
Yes, it is. We're looking at the bottom. That's what I've been measuring.
Oh, you did it! There you go. Nice. So this time, it was 43.4 drops. Procedure, part 3, trials 1 and 2. This time we're going to use the burette and add 2 milliliters of 0.1 molar sulfuric acid to the test tube. Add our 2 drops of phenolphthalein, use the pipette and add our 0.3 molar sodium hydroxide, slowly drop by drop, counting the drops. And when the solution changes color, we're going to record our results, repeat the procedure, calculate the average again of the number of drops of sodium hydroxide needed from trials 1 and 2 of procedure part 3. And then lastly, we're going to clean up as directed and wash hands.
Yeah, I think that's just the side Oh, what? Oh. Wait, shake more.
Yes, I am. No, you literally voted for him.
It's okay.
Because you can't be it. He wasn't here and he didn't want to be it.
What? Shake more.
Because you're a junior.
Ah.
That was good on the field.
19.
There we go.
Yeah, that's true. That's true. I saw it.
One more. Please, go away.
Oh,
I've lost count.
let's go.
We lost count.
I didn't understand it.
Solve!
Okay, I think you got it.
Oh wait, there's a bubble on top and then pink on top and clear in the bottom.
Oh, cool.
Yeah, that's done. Okay,
Good job, guys.
Put it down. Put it down.
So this time we needed 57.2 drops. Analysis. So analysis part 1, examining data. What was the average number of drops of sodium hydroxide required to consume 2 milliliters of hydrochloric acid? And also, what was it for? So here are our average numbers. And then we're going to go ahead and average for our sulfuric acid. So here we have our averages for the hydrochloric acid at 2, the hydrochloric acid at 4, and now finally the sulfuric acid at 2 milliliters. So now we need to analyze our results. And we want to see if we can compare our responses in analysis part 1, which was where we determined our average number of drops required for 2 milliliters and 4 milliliters of hydrochloric acid, and see what we can find for a ratio. So our ratio in this case was there 2 to 4 for our volume, which means that we had 2 milliliters to 20.4 drops and 4 milliliters to 43.4 drops for hydrochloric acid and sodium hydroxide. This tells us that the number of drops doubled when the volume doubled. That's roughly what we see, and that's what we should have expected. Now what we want to do is compare our results to analysis and interpretation items 1 and 2. And is there a difference in the average number of drops? What is the ratio between the two numbers? Is it 1 to 1, 1 to 2? So let's have a look here. Our averages here show that we have 2 to 20.4, 4 to 43.4, and then at the bottom we have 2 to 57.2. All right, so what does this really mean? It means that the number of drops needed was almost 3 times greater with the sulfuric acid, because it's almost 60. So let's have a closer look. Ratios. Our volume of hydrochloric to the drops of sodium hydroxide was 2 to 20.4. If we want to take that down to 1 milliliter for simplicity's sake, we have a 1 to 10.2 ratio. And for our 4 milliliter volume, it was 4 to 43.4. And if we bring that down to 1 milliliter for simplicity's sake, we have 1 to 10.85. And the average of those is 1 to 10.5. So on average, it's going to take 10.5 drops of sodium hydroxide to completely react with 1 milliliter of hydrochloric acid. So for our sulfuric acid, we had 2 to 5.72. And again, if we bring that down to 1 milliliter for simplicity's sake, we'll find that 1 milliliter of sulfuric acid required 28.6 drops of sodium hydroxide to completely react. So it takes 10 to 11 drops of 0.3 molar sodium hydroxide to fully consume 1 milliliter of 1 molar hydrochloric acid, and it takes about 29 drops, if we're rounding. We could say 28 to 29 of 0.3 molar sodium hydroxide to fully consume 1 milliliter of 1 molar hydrochloric acid. So taking a deeper look here, we'll put these ratios over here. These are our average ratios. But there's another ratio to consider, and that's the coefficients. So here we have a coefficient of 1, and next to it, we also have a coefficient of 1 for our reactants. Here we have another coefficient of 1, and then in front of our sodium hydroxide, we have a coefficient of 2. So what does this mean? Our hydrochloric acid to sodium hydroxide, our coefficient ratio is 1 to 1. Our volume ratio was 1 to 10.5. And for our sulfuric acid, our coefficient ratio was 1 to 2. And our volume ratio was 1 to 28.6. What does this mean? Well, the factor by which the ratio of coefficients differs should be the same factor by which the ratio of volumes differ. Well, what could be going on here? If we have a look at these ratios a bit closer, we'll discover here that we can take our data and see by which factor the ratios differ. So for our hydrochloric acid trials, our ratios differ by a factor of 10.5. And for our sulfuric acid trials, our ratios differ by a factor of 14.3 because we have 1 to 1 and 1 to 10.5, 1 to 1, and 2 to 28.6. So the difference, if you divide that 28.6 by 2, that's what you're going to get is the 14.3. So it's these numbers that we need to take a closer look at. Using the data from our hydrochloric acid trials, which showed our ratio of sodium hydroxide coefficient, which in this chemical equation is 1, to the volume of drops differed by a factor of 10.5 drops. We should expect our sodium hydroxide volume in drops in our sulfuric acid trials to differ by around 21 drops, as the coefficient for sodium hydroxide in this chemical equation is 2. So what we're saying here is that if our factor by which the ratio differs is actually 10.5, and we apply that data, which we got from our first trials with hydrochloric acid, to our second trials with sulfuric acid, we should expect that number to be 21, not 28.6. Likewise, if we use the data from our sulfuric acid trials, which showed our ratio of sodium hydroxide coefficient, which in this chemical equation is 2, to the volume of drops differed by a factor of 14.3 drops, then we should expect our sodium hydroxide volume in drops in our hydrochloric acid trials to be around 14.3 drops, as the coefficient for sodium hydroxide in this chemical equation is 1. So again, if we say that our factor by which the ratio differs is actually 14.3, which is the data we got from our sulfuric acid trial, then we could apply that data to our hydrochloric acid trial, and we should expect that number to be 14.3, not 10.5. So this means that this 10.5 could actually be 10.5 to 14.3, and this 28.6 could actually be 21 to 28.6. So the average of 10.5 and 14.3 is 12.4, and the average of 21 and 28.6 is 24.8. So if the actual factor by which the ratios of coefficients and volumes differ is likely between 10.5 and 14.3, taking that average, our new average ratio becomes 1 to 12.4. And if the actual factor by which the ratios of coefficients and volumes differ is likely between 12 and 28.6 drops, taking that average, our new ratio becomes 2 to 24.8. One to 12.4 equals 2 to 24.8. So our results are a bit off. The ratio we expected to see in Procedure 3 should have reflected that the relationship between the sodium hydroxide coefficient and the volume of drops of sodium hydroxide required to consume the acid were proportional to the ratios we observed in Procedures 1 and 2. The coefficients in the balanced equation were a 1-2 ratio. The same volumes of acid were used, but different amounts of base were required. With the inclusion of all class data and additional averaging, we were able to see that we did get close to that ratio. Applying conclusions. Based on your observed results, how many drops of sodium hydroxide would be needed to react completely with a 2 milliliter sample of nitric acid? In order to react completely, our overall average data suggests that about 12.4 drops of sodium hydroxide were needed for a 1 milliliter sample of acid whose coefficient is 1. As one cannot accurately divide the volume of a drop using a pipette, we conclude that 13 drops of sodium hydroxide are needed for a 1 milliliter sample of acid whose coefficient is 1. Therefore, we hypothesize about 13 drops of sodium hydroxide would be needed to react completely with a 1 milliliter sample of nitric acid. Therefore, about 26 drops of sodium hydroxide would be needed to react completely with a 2 milliliter sample of nitric acid. Great job. Be sure to complete your lab report using this data, and it will be due next week when you return to class.